Hello everyone. In this set of videos we are going to review a set of topics which are classified in our textbook as important details of stability analysis. So this is kind of a catch-all topic, and specifically the three things we're going to talk about is location of critical circles and dealing with local minima, something that we've explored a fair amount, but it's a little bit more of a deep dive into that. And then how to deal with tension in the active zone and certain combinations of forces in the passive zone. That the active zone is at the top of the slope, the passive zone is at the bottom of the slope. And so let's jump right in. Let's talk about the location of critical circles. And so just to quickly summarize, the automatic searches that you do with UTexas ED can often lead to local minima. We've seen that in our in-class exercises. And the critical surface that you find is dependent on the location of the initial trial surface. And so you need to be really careful that you don't if you have multiple materials and even with a single material, there are certain cases where you can get a local minima. But you have to make sure that you're satisfied that you've explored all of the potential starting locations for circles and you found the global minimum factor of safety. And but as you do that, a little bit of background and knowledge of the typical location of critical surface will help you be a little more knowledgeable about how to guide that process. And so, but let's start with infinite slope. This is what we get for cohesionless soils. Or if you have cohesionless soils and you're doing an infinite slope analysis, the critical surface is simply the layer with the lowest phi value, and the friction angle is tan phi over tan beta, where beta is the angle of the slope. So that's like a really easy case. If you have purely cohesive soil, so phi equals 0, it's undrained analysis, then the critical surface is at the depth with the lowest ratio of C divided by Z, where Z is the depth from the top. And so if you have, if that's a single layer or a single material, it'll just be at the bottom of the material. And if you have multiple layers, you just check at the bottom of each layer and to find which one has it's going to be dependent on the combination of both C and Z in that case. For circular surfaces, I'm not sure this is something that we explored in too much detail, but if you have a slope that is cohesionless, where the C or C prime is equal to 0, then the critical solution will correspond to the infinite slope solution, where the factor of safety is tan phi over tan beta. And if you plug in the geometry for this and the material properties, let's say a simple slope like this, where you have a phi value but C is 0, you should notice that when it converges to the critical circle, it will be some circle that just barely skims the surface of the slope, and the center of the circle will be out at some really large distance. So it's a large circle, large diameter circle. And so what it's simply doing is converging to the infinite slope solution. The fact of the matter is, if you have a simple slope like this and the cohesion is 0, there's no point whatsoever in setting up UTexas and running a full-blown limit equilibrium slope stability analysis. You can just do it in the calculator. It's tan phi over tan beta. Okay. If you have purely cohesive soils, so phi is equal to 0, if you have a steep slope, that is a typo. That should be beta less than no, excuse me, that's correct. Beta, the slope angle greater than 53 degrees. Then it's either a slope circle or a toe circle. And we discussed this earlier when we went over the stability chart. But if it's a mild slope, where the angle is less than 53 degrees, then the circle generally goes to the bottom of the layer, and the center point of the circle is located in the middle of the slope. So this is all semester long I've been telling you that a good place to start your search for a critical circle is halfway, where the x value is halfway up between the toe and the top of the slope. Well, there's good reason for that. That's generally where the critical circle center point is for the phi equals 0 case. Now, if phi is not equal to 0, it'll deviate from that, but that's generally where the critical circle happens, which is kind of interesting. Now, in the general case where phi is not equal to 0, then it has been shown that the center of the critical circle is somewhere in this band where you go to the slope midpoint, and if you draw it, this line is perpendicular to that, and then if you go 2 times phi d, that'll give you this line. And so this is a good place to start your circles. It's going to be somewhere in here. Now, I would never go to the effort of calculating the geometry of this, but it's just interesting to know, because as long as your starting circle is somewhere up in that domain, it should be a pretty good starting point. And so, yeah, I generally recommend going halfway between here and here in x, and then up at least 2 times the slope height from the base down here for your starting circle. And so, recommended strategy, pick the location of your circle using the guidelines from the previous slides. For the radius of the circle, try a toe circle. A toe circle is a circle that passes just through the toe of the slope, and sometimes that's the critical circle. But if your starting circle doesn't, if you don't do a search with a circle starting at that location, it may not happen to find it. So it's often a good idea to explicitly try that. Now, in the full version of UTexas, you can just tell it, give it the coordinates of the toe of the slope and tell it to start that. In the educational version, you just give it the elevation of the bottom of the circle, but you can trial and error to come up with a circle that passes through the toe of the slope. And then try a circle tangent to the bottom of each of the soil layers, so that once you've covered those bases, you probably will have your critical factor of safety. If you have a non-circular failure surface, one strategy you can use is find the critical circular surface and then add a series of points along the circular surface and use that as a starting point to search for a critical non-circular surface. If you're dealing with a really important slope stability analysis, this is probably a good strategy. A circular surface is generally close to the critical surface, but not exactly. And so starting with a circular search and then making it non-circular and letting it warp itself through the search process until it finds the true critical non-circular surface is not a bad strategy. Could give you a really nice global minimum factor of safety. And as we've seen, if you have cases with thin, weak zones, typically horizontal, then you make your starting non-circular surface coincide with that weak zone. And that will often give you the overall critical factor of safety. And so we've seen cases in our in-class exercises where you can get multiple minima depending on how you start your search. This is an example of one. If you start with your beginning circle tangent to the top, it will converge to a solution there, but if you start it tangent to the bottom, it will converge to a different solution. And so this is one of the exercises that we'll go over in our in-class exercise. But you'll encounter a number of cases like this, and so the bottom line is just make sure you try a variety of starting locations, typically at the bottom of each layer and then through the toe of the slope if you haven't done that with one of the layers.